let's start back up again. Okay, so we're going to switch topics now. We're going to something a little bit easier, a little lighter weight. This will also help you with Java. It's the concept of threads. As I mentioned before, we have threaded applications, and we have one thread that works at a time. We can actually create multiple threads within the application and switch back and forth between them. We looked at how we did it with intents. This is a little different. This is from a Java programming perspective. So why threads? Basic concepts of threads, the 3 different variations on the theme, as well as some related topics about race conditions and synchronization, and hopefully some helpful hints to help you create some multi-processed concurrent running threads programs. And I have a project I put together that's going to demonstrate the thread concept. If you have not found this lecture yet, it is out here in the bhacker.com web directory under the tutorials for Android phone application development. You'll see in the tutorial section. Oops, looks like some people are on the internet. It's trying to download. At least I have internet connectivity, which is a bonus. If it waited and it loads, it'll be down here in the list somewhere. You don't have anything? I should consider myself lucky. Alright, thank you. Anyway, it is in this directory under tutorials if you're able to see it. It's called Threads. There's Threads and there's Threads 1. Multi-threaded lecture, yes. Alright, so the motivation for concurrent programming, the pros and the cons. Let's get back. Okay, so the pros, advantages to given single processor systems is efficiency. So we're creating multiple threads to get multiple activities performing simultaneously for efficiency purposes. When I say simultaneous, that's kind of a nomenclature. That's really not right because nothing is running simultaneously. It's one thread at a time. But we'll see how that's working. For convenience as well, a clock icon as an example in terms of, and I'll show you the example of that. And for responsiveness, responsiveness is probably going to be the biggest bonus to using multiple threads. Some devices have multiple CPUs and cores, so you can actually run multiple threads simultaneously. And you can find out via the runtime get runtime.available processors. And you can figure out how many processors. There's a lot of Android systems actually that has dual cores on it. So for dual processing systems, you know, it might actually be good. The cons to it, significantly harder to debug and maintain than single-threaded apps. Yeah. Well, you're just adding more threads to it. So this is what I call more of an advanced topic. Something a lot of people will not get to unless they actually find a need for it. So steps for concurrent programming. First, make a task list. So we have a list of tasks that we're going to basically put into a pool. So we use a executor service task list is going to be equal to. Can we keep it down in the back? I feel like I have to start yelling. I'll just wait for people to stop talking. Okay, good. Now we're ready. So executors.new fixed thread pool with a thread pool size. So we're making a pool of threads that we're going to use for different activities. The pool size is the maximum number of simultaneous threads. So for many apps, it's higher than the number of tasks. So each task has a separate thread associated with it. And then there's any number of different types of thread pools. But this is the simplest kind of abstraction, which is what I'm going to show you in the sample project. So then second, we're going to add the task to the list. So we have 3 options for adding the task to the thread pool list. Make a separate class that implements Runnable, and we're going to see that. Or make instances of the class and then start the threading via the task list.execute. New my separate Runnable class. And then have your existing class implement Runnable, which is another option. So start the thread via the task list.execute this. Or use an inner class, as we mentioned before. So the inner class is another option that you can do for this as well. Why is it so loud in this room? Where? Okay. So approach number 1. We'll create a separate classes that implement Runnable. So the thread mechanism number 1 here with a separate Runnable class. This actually applies towards the same concept with non-Android. Java is Java, so it's the same concept actually. Make the class that implements Runnable. So there's no import statement needed. Runnable is in the Java language. So you put the actions to perform in the run method, and in the run method here is going to have my runnable class implements runnable. And then you start out with the void run and you run something. So let's take a look here real quick actually at the there's an example that's out on the website that you can download it once you get internet access again. If you don't have it yet, don't know what happened here. Here it is. I have internet access. We have a threaded, these are the two lectures we're going to go over. This one's the bigger one of the two. This one's a kind of a short follow-up one. Tutorial 1, Tutorial 2 with a threaded, multi-threaded solution. So this is the example I'm going to show you in a few minutes, which is the one you can hopefully get to. If we take a look at the multi-threaded solution, and if I go into the list of classes here, there's several different activities that are listed. If you run it, and I have it running right here, you can see that each one of these buttons is for one of these different classes. So it's a lot of different examples that are all put together, which is not too bad. There's one that does a race condition, no threading basics, URL checker. So I'm going to look at the threading basics one. If we take a look at the kind of the sort of the implementation of this, if we look at the activity utilities, we're going to see essentially all of the different classes that are going to extend other classes, and the nesting of the classes as we've got in here. And threading basics activity class here, where we've got the implements runnable. Let me make the screen a little bit bigger so you can sort of see what this is alluding to. Let me close this one here too. So what I've done is I've opened up threading basics activity.java, which is the first one we're going to look at actually. And you can see that it extends activity and it implements runnable. Runnable is the interface. And so inside, the app's going to look the same as before, but we're going to create a loop limit of 5 and use that as a variable for threads. Initialize the app using the same techniques as before, using the onCreate method, and then onCreate running, and the layout's going to be threading basics, which is going to be the interface for it. And start a counter that uses option number 1, a separate class that implements runnable. So what we're looking at then is in terms of the code that we're going to be looking at. And here the thread pool is set for 50, and it's going to task list that execute new separate counter. And we're basically going to keep a counter for each one of the threads that we're going to do in this loop, and we're going to use the pool to manage the activities that are being performed by the class. And so if we take a look back here, and this is these are the examples here that are being referred to here. So if you wanted to see it live, I'm just showing you where you can actually locate that. So in order to make it runnable, we can implement runnable, which is what we just saw live a few minutes ago, which is why I wanted to show you that. That's the interface for it. And then in a regular application, we could go void run, and the onCreate we can actually is the substitute for that. In an Android app, we would put our code in there to onCreate of the process. And then create the instances of your classes, or lots of instances if you have lots of threads that you want to use it for. And then pass the instance to execute service.execute, which is what we're doing in that example, which means, and that's just a counter that's keeping track of something, numbers or integers or something, to do something. And so what we can do is break out the activities that are being performed by the app into these separate different threads and have more of a multi-threaded application. Why do we do that? Because we can get stuff done faster than having to wait for something to start and stop and start and stop. We can just have them all set and ready to go, queue them all up, and then just have them run. So the number of simultaneous threads won't exceed the maximum number if we set the list manually for us. So then we have a separate runnable class. Here we have extends activity, but here we have in here the code here to set up the execute service, and then we're going to have the task list dot execute some class. So in our particular example, we're just creating instances of classes that are running. So it's going to be separate counter, separate counter, separate counter. Separate counter is the void separate counter is the method that we're running here, where we're going to click a button, we're going to have a separate counter. It's just going to basically create. So if I run this, you can sort of see what happens here. This is the threading basics example. If I run this option here, We can see the DDMS window here for the output. It's just going to be here using the 3 different methods of putting it together. All 3 methods have slightly different implementations in terms of where we're putting the implements runnable. Using a separate class for it, main class that implements the runnable, or using inner classes inside. They're all doing the same activity. If we open up the DDMS window, we can sort of see what's going on when we run the activity. And here it is here. We make this screen a little bit bigger. We can see the system output. It's just basically our counter that's looping through, creating these separate instances of classes. So the threads aren't really running anything. Instead, they're just demonstrating the concept. So if we do this one here, click on this one, it's just going to loop through. You can see it looping in the background. It's really doing the same thing, accomplishing the same task, but using 3 different techniques. Can we shut the back door maybe? It's extremely loud in this room. It's irritating me. So maybe, where's my TA? Can we have a little noise control going on here? Can we shut the back door? Or, oh no, he's beat you to it. Okay. Thank you. Alright, so how are they implemented? Well, the 3 different ways are from the class itself. So the first one here, thread mechanism number 1 is a separate runnable class. So what we've done is inside we're going to implement runnable. It's a separate class that's going to run it. And in the runnable class, we have this little template code that runs that's going to start some thread sequence. So create a pool of threads and then execute them with some task. In our particular case, we're just running a counter. We're not doing very much to it. In terms of the example here, this is what the code is that is running inside of the example I just showed you a few minutes ago, the basic threading class that we just looked at, and we just watched it run actually a few minutes ago as well. It's a separate counter that's sending it, so the method that's associated with the button for the onClick event is going to run this method. This method is going to run the threads, and each one of the threads is going to make a new instance of the separate counter and give it a number, and then basically simulate the running of multiple threads in a task list that's going to occur. And so we use implements runnable on the class itself for class separate counter. And then inside we have the void run. So we have the void run inside of the separate counter class that's being implemented. Oops, I don't like that one. Let's go back to the Java code. Separate counter is right here. Separate counter is being run inside of this method that gets clicked. When that button up there gets clicked, and in that button we have this class here, and this class here is basically what implements runnable, and in here we have run. So the method that implements in terms of the interface runnable is the run void run method. If we don't implement void run, we don't implement the interface correctly. So, and what is this doing? It's automatically creating our multiple threads for us. So we have our thread name in here, and thread.current thread get name. It's going to be the name of it. What's that going to be? It's probably a process ID, something associated with a process. And then system out, we're going to put the thread out name out there, and then we're going to sleep for a second and then run another thread out. So if we look at the output that comes out of here, we have pool 3. So for our system out, we have pool 1, thread 1, and the numbers associated with it, thread 2, thread 3. So it's all coming out of multiple pools, and we have multiple threads inside of multiple pools. And doing nothing more than printing something to the screen. It's not really doing anything. And the system out's coming from each one of the threads that are running. So it's not, rocket science-y. It's essentially just demonstrating the concept in terms of what's going on. And it's actually using a system out, which is kind of interesting because this is plain old Java programming. And it's the same old method that you would do in a non-Android app. But you can take non-Android thread concepts, apply it to an Android app, and run it as we're seeing it inside of an Android app. It's the same concept. So if you're familiar with this from a Java programming perspective, then it's the same, which means we can also synchronize, and we can do everything else for inter-process communication. And usually people wonder why in the world we want to do that. Because we have the same problems on an Android app as we do on as a regular JVM app. it runs on the slower side, so we can create multiple threads, create thread pools to get work done faster. So it just adds more processing, more resources, more resourcing time. The more threads you have, the more CPU time you're getting for your app, essentially, or for your program, because you have multiple processes running, which is kind of the concept of Windows and multi-threaded application development from any other platform as well. So then we have a helper class in this particular case. So this one here is just an example of the class itself that implements Runnable, and this is the separate counter class that's being run by each one of the threads in the main app. The helper class here is for the thread utils, and it's going to perform a pause for us. So we're going to try and sleep the threads. So thread.sleep here, and then catch any interrupted exception that might exist from that, and then uninstantiate it, essentially private, by going private thread utilities. So the results of the program looks like this. We just saw it running live a few minutes ago, but this is now color coded, so you can see the thread 1, 2, and 3 in different colors, and then from each one of the pools where that's going to come out of. Pros and cons of this approach. Advantages, well, it's loose coupling, so it's not too much that's going on between them. You can change the pieces independently. Well, as we saw before, in the activity, it is just running the class. So if we take a look at the Java code and we look at the thread basic activity, that's loose coupling. Put any class you want in there. It can do any functionality that you want. So you could set up a main activity that's going to run some things for you. That could be a higher level menu. Could be a menuing app that's going to run different programs for you or schedule different things for you. Maybe run services or something, or turn services on and off or something. That could be all facilitated through a thread pool. And so you can reuse the Runnable class in more than one application as well. The passing of arguments, if you want different threads to do different things, you can pass it different arguments, different classes to run. They don't always have to be the same class, which stores them in an instance variable when a method is being used. And then there's also a little danger of thread conditions, or race conditions, excuse me, because the threads are running one after the other. So there's not really going to, it's an ordered list. It's not really going to have any kind of multi-threaded race condition. And there's an assumption here that you understand what a race condition is. So when two threads try to go for the same resource simultaneously. You'd have a race condition if two threads were trying to send a text message, or they were trying to send an email message or something. They're going to collide, or one of them's going to work and the other one's not going to work or something. If you have that going on, you're going to have some unpredictable behavior in your app. So there's also the condition of starvation and deadlock that also occurs. All the same problems you have with regular old thread processing are same scenarios you have with Android thread processing. However, we have in Android, we are able to use Java, which has synchronize. So as soon as you synchronize something, you've now gotten rid of starvation and deadlock, and you still have race conditions, but you definitely have solved a lot of the other problems for you automatically. So thread programming in Java is a lot easier than C or C++, if you're familiar with that. A disadvantage here is hard to access the main activity. If you call the methods in the main app, you must pass the reference to the main app to the Runnable constructor, which is going to store, which stores it, and then make the methods in the main page be public instead of making them private. So approach number 2, the main app implements the Runnable. So here we had a Runnable implementation of a class that's being run, so the main app doesn't have to implement Runnable. Second choice you have is just to make the main app implement Runnable, and then anything you put inside of that call from it, it's going to be runnable. It's going to be threadable. So in terms of the syntax, we have a shape here, and so interface shape is an interface, and then we're going to implement shape from a circle. So you can implement many interfaces that actually come from this. So we don't necessarily have to review the benefits of interfaces, I hope, at this point, because you're going to be familiar with that, because you're going to have interface questions on the final tomorrow. So, and sum equals sum.get s.get area is just an example here. You're going to have a get area part of shape. So you'd put shape would have an area or a get area interface method that's associated with it, because it would be impossible to actually make a generic one for a shape. So it's going to be different for a rectangle, triangle, circle. So that makes it great for example, actually. Now, in terms of making the main app runnable, you can have the main app implement runnable. So you put the actions in a run method of the existing class. So we have my class extends activity implements runnable, which makes sense. So passes the instance of the main class to execute. So this is what's been runnable. So we're taking this and we're passing it to the task list dot execute this because we're now runnable, which means we're multi-threaded. So many differences from the previous approach. It's good. The good point is that you can run as easily, and run can easily call methods in a main class since it is in that class. It's not outside of it. But if you run access as a shared, any shared data, any instance variables, and worry about maybe a conflict or a race condition might exist in terms of the update of those variables, and very hard to pass arguments so the task starts off the same. So. In terms of the template code, this is what it looks like. The thread activity that extends activity implements runnable. Run would basically don't update the UI, run something in the background because what will end up happening is the UI will freeze on you. So you're going to basically create a task list. The same code as before actually, but you're going to run it with this instead of executing it with some sort of a class name because this is runnable versus the. In order to execute a service, execute something, you have to be extending runnable, implementing runnable. So it's either going to be the class that's implementing it or the class you're trying to run that's going to be implementing it. So it's a lot more generic if you make the class run it because everything will run because it's already extending or implementing runnable. So let's see. Here's the code for it. Here's just a slight change in here. Instead of putting a class instance in here, saying a new whatever that was called. Now we're just saying this. So it's going to run this again. So, and then the same output as before. So if you take a look at the code for it, you'll see inside of here the 3 different techniques that are demonstrated. But in the next one is going to have this in here instead of new separate class or separate counter. Oops, where'd it go? Here it is. Pros and cons of this approach. An advantage, it's easy to access the main app. It's actually easy because you can run anything inside of it. You don't have to worry about, is this class runnable or not. And the run method is already inside of the main app, so you can access any public or private method or instance variables, although you do have to make sure you don't have any race condition that comes up. Tight coupling, you run the method is tied closely to the application. Well, it's inside of the application. You can't separate it out, so it's definitely tighter coupled. Can't pass arguments to run it, so either at the start of the single thread only, quite common, or all the threads do very similar tasks or the same tasks, because you can't really start anything new inside of it. And in danger of race condition, as mentioned before, because it could be at the same method, could be using the same. You have the same this running simultaneously, updating this is memory, updating the variables, running the methods. You're going to have some conflict with 2 of the threads accessing the same method or the same variable simultaneously is going to destroy the value. So race condition can cause corrupted data members of the particular class. So modifying shared data. Approach number 3 is the inner class that implements Runnable. If you guys think about all of the action listeners we talked about last time where we had the 3 methods, these are the same 3 methods. Either you put the action listener on the class, you put it inside of the class, or you put it on methods inside of the class. It's really all the 3 same techniques over again. But this time it's applying towards thread synchronization, or excuse me, multiple threads running. So to review the inner class concept, which we saw before, you put a class inside of a class. So the inner class is inside of the outer class. So, in terms of the runnable inner class, you just add implements runnable to it. So it's the same thing as before. So whether you put it on outside classes, inside classes, or the class itself, you're accomplishing the same task because you're always implementing the runnable and you're implementing the run method inside of it. So it puts the actions inside of the method of the inner class here. So pass the instances to the inner class to execute it. So new sum inner class, which is this sum inner class that we defined here. This is the inner class or whatever we put inside of the main class is going to be in our inner class. So an inner class is just a class that's, just to review the concept, is a class that's defined inside of a class. So it's inner, belongs to the class. Is it still accessible outside of the class? Depends on the scope of the class. When you put it inside of the class, it's only visible inside of the class. It's not a public class. So in terms of the template here, we're doing the same thing, but now we're going to put it on a new runnable class. It's an inner class. So the syntax is actually the same as the outer class. We're just putting it on the runnable inner class. And it's also implementing runnable, as you might imagine. And here's the runnable class that's inside of the class. So the thread mechanism here is basically doing the same thing as before, where we've got the thread extending activity. On the onCreate method, we're setting everything up. And then on the inner class here, the void inner class, we're creating up the task list and we're setting up the inner class. And then the inner class is going to implement runnable. Somebody's going to implement runnable, either it's the inner or the outer, or it's the class itself, or this. And it's basically going to implement the run method as before. And what is it doing? I was creating a random number for the thread utility. So the output's going to look the same. Pros and cons of the inner class: it's easy to access the main app, what's inside of it. Methods in the inner class can access the public and the private data member of the outer class, which is why we nest classes. It makes it a little bit easier for that. And you can pass arguments to run it. And disadvantages: it's very tightly coupled. Well, it's inside of the class. So it's the same problem as before. When you're making the entire class runnable, everything is tightly coupled. And you can run the method that's tied closely to the application, which isn't what you're going to have to. And there's also the same problem as before. In fact, all of them have race condition issues. Because the race condition is what's going to happen when you have multiple threads running the same activity, essentially. So summary of the approach is the pros and cons that are associated with it. The separate classes that implement the runnable can pass arguments to run. And they cannot easily access the data in the main class because they're separate classes. They don't belong to the same class. And usually no worries about race conditions because they're all going to be running separately. And because you're going to set the order and they're going to run one after the other. The main class implementation runnable can easily access the data inside of the main class because it's the class itself that's made to be runnable. But you can't pass arguments to itself, so there's no argument passing going on. And there's usually no worry about race conditions, especially if you synchronize it. And then the inner class implementation can easily access the data inside of the class, the same as making the class runnable. Can pass arguments to run, and I must worry about race conditions though, because it's running as separate threads inside of the main, so it's all accessing the main class's data members and member functions. So race condition, as I kept mentioning before, there's a keyword called synchronize that's used in synchronization that's used to get rid of conflicts that we have for deadlock and for race conditions. So the idea is the same as in regular Android programming. So you apply it towards Android platform instead. The idea here is you write the code that assumes no other thread runs between the certain steps, which would be the critical region, critical part of the code. But if the thread is interrupted in the wrong place, then another thread changes some of the data, you get a wrong answer that might occur. That's a race condition that's describing there. Typical scenarios: you modify the shared data and assume that the next thread sees the new result, but they may not. You might be working with an older result. So you can read value and then increment it. You assume that no thread runs between each one of the reads and writes when you're incrementing it. Same thing happens with the database connectivity, actually, which is why you have synchronization built into the transactions that occur, which is what you have to think about when you're going to work with multiple threaded applications, whether it's an Android or a regular Java application. So you can read shared data and then use it, and then forgetting that it could be changed by something else that's using it, and you can come out with some wrong values. So here's a race condition example, and we have one actually built in. In fact, the differences between the two is just that the methods are now synchronized on one and not synchronized on the other. So the example is actually quite easy when you look at it. Here's the race condition activity. If we go out to the site, go out to the project, you can see I have race condition activity underneath it. A race condition activity doesn't use synchronizing at all. So we take the same code and then we synchronize it, and we have a non-race activity. Runs a little bit slower than the race activity. If we take a look to see, well, what options are we looking at? The first one here was giving us the threading basics, which was giving us those first 3 examples. The next one we have is the race condition versus the no race condition. If we try the race condition here, we're not going to see anything in this window because we're using system outs with it. So instead we're going to see in the logcat or the DDMS window. So we have 2 threads that are racing with each other. Essentially they're going to deadlock, or they're going to have some corrupted data. If they're looking at a piece of shared memory when they're both updating it or reading and writing to it, one of them's going to overdo or redo something or change a value that was shared by another. So this one hasn't deadlocked on me, it just ran for its normal amount of time. Sometimes it will actually deadlock on you depending upon how you're doing it. And you can compare that with no race condition. No race condition, you can't tell, it actually does run a little bit slower. I see it working in the background here. It's going to run in a loop and do the same activity as before. And that one I hit twice actually, which is why it happened. So this one's starting an intent, and the intent's going to run the thread that's going to do a counter essentially. It just prints out I'm a counter 0, I is 0, and then set our current item to 1. So then I'm a counter 1, and then each one of them in a race condition is going to maybe change the number or not increment it correctly because it's going to have an old value back and forth. So what's the code actually doing on the try race, which we just ran a few minutes ago? It's going to create a pool of threads, and it's going to execute each one of the threads. And the threads are simply just doing a system out, setting the current value to something, and the current value is going to be some counter that we're keeping track of. So the latest thread number in this particular case, and it's going to be incrementing it +1, +1, +1. So if they're both running simultaneously and they're both incrementing it, you can see where one would hold a 0, the other one would hold a 0, one would update it to 1, the next one would update it to 1, but it might be changed to 1 if it's like 2 from the other one who's already done 1 to 2 to 3. So they're both of them are going to be working sort of against each other in a race condition to see who can finish first. And the incremented values are going to be off. So what's wrong with this code? Well, I just explained it to you. Here it is here. Here's the physical effect of it. So setting current value to 0, I'm counter 0, I is 0, setting current value to 1. The numbers are going to be off. So occasional output might be something of this nature, where you might be setting it from 36 to 37 to 38, but they must be setting it to 38, they must be setting it to 0. So depending upon what value of the shared data they're currently looking at, they might be incrementing the wrong value associated with whatever turn they were on. So, which is what you get when both 2 threads try to read and write simultaneously. So this is the one that's not synchronized, so they both have the ability to read the data simultaneously. The solution to this is to do things in a single step instead of doing things multi-threaded. So in this particular case, we have an incremented counter here, and we're going to run one, and we're going to run the next, run one, run the next. Arbitrarily contention for the shared resource, we're just taking turns. That's actually, in Unix they call that a mutex, and you're locking and you're unlocking. So you basically only have one thread changing the value and then lets the value go, and the other thread can touch the value. So you're switching turns back and forth, which is not what I'd call multi-threaded, but it's a way of sharing the resource. So in here, a contention for the shared resource is just arbitrary. You can actually use the keyword synchronize. So if you have synchronized an object, then you don't have to do things serially or in one step at a time. You can do things together and then let the JVM synchronize it. So only one thread is able to go in and access the critical region at one particular time. So, and from fixing the previous example here, we just go synchronize this So we can synchronize this, which means synchronize me if I'm the running thread or if I'm the running class, which means don't let somebody else access my data members or my mem functions simultaneously. Which means if it's open and being used by one thread, it's not available for somebody else. It's not a lock. It's just basically setting the order to make it serial. So synchronize makes something that's not serial, which means it puts an order to it. So our race condition here is synchronizing a section of the code by going synchronize some object and put some code in here. So simplistic interpretation, once a thread enters the code, no other thread can enter in until the code is finished, until the first thread is finished, which is what synchronize is going to do. In terms of a stronger implementation of this, once the thread enters the code, no other thread can enter the code, and the code that is synchronized is using the same lock object. So it's kind of like putting a lock on there. So synchronize this, synchronize that. It's like doing an automatic mutex, actually, from a Linux perspective, but it's Java, so they use the keyword synchronize, which is kind of interesting because you don't have to do counters, you don't have to do anything, you just add synchronize to everything. It just means if it's doing something on a piece of shared memory or something, then serialize it instead of making it run. So synchronize, public synchronize void some method. So instead of putting synchronize on the running of some object or some, some instance that you've created, you can actually just synchronize the method. So public synchronize void make some method to synchronize and implement the method. Notice it is equivalent to synchronize this inside of it. So some people like this syntax, some people like this syntax. I would actually just synchronize the method, not really synchronize inside of the method. That way when I easily look at the method, I can kind of see in the footprint of the method that the code has been synchronized. This, believe it or not, saves you thousands of headaches and troubleshooting issues versus C. So thread synchronization in Java is a lot easier. And everything you do from a Java console or just regular old Java app works in an Android app. In fact, you can use all sorts of different thread concepts to create client servers, which is what we're going to see in another example of, a server app, a client app that works on an Android platform instead of a computer, which is kind of interesting actually when you think about it. What is that good for? Sending and receiving information back and forth. It's kind of like text messaging, where you're not using a text messaging service, you're just going over a network and you're pinging different devices and sending and transferring things, pictures and files and stuff. So, helpful thread-related methods. We have current thread to get the current thread. Gives the instance of the thread that is running, current code. Thread sleep. You want to make a thread stop for a second, but calling the thread puts it to sleep. Useful for non-busy waiting and all kinds of different code. Not for multi-thread code. We have synchronized for that. And you have to catch an exception, or you can ignore it if you're going to sleep it. Some thread.get name, some thread.get ID, get the name and ID to basically identify it, print it, use it for debugging purposes. So methods for the executor service, we have the execute, which we've seen in some of the examples already, adds a runnable to the queue of the task. Shut down now, which is kind of similar to ending a process. Wait before you terminate it, wait termination, which is it's going to be blocked until all the tasks are complete, and then it's going to be shut down after the tasks are complete. Why do you want this? Because you can essentially mimic services and things, send a message and then shut down, then have another thread open up to receive the message and then shut down or something. And then submit, invoke any, invoke all, different variations of the callable instead of runnable. So in terms of callable, we have callable and runnable. So runnable means run methods. So a method runs in the background. No return values, but can have side effects when something is running in the background. Use execute to put a task into the queue. Or callable methods run in the background. It returns a value that can be retrieved after termination with a get. So runnable just runs it. Callable actually returns it. Usually calls have a return associated with it. You can use submit to put the task into a queue. You can use invoke any, invoke all to block until the values actually occur. or become available. So if you list the links, if you have a list of links from a web page and you want to check the status, are they good or are they bad, then you can submit them to a task queue and then run them concurrently and then invoke all. Will let you see what the return values were. So this next example actually runs and checks a bunch of links to see which ones are good and which ones are bad. Well, what are we going to do? We're going to put in a thread pool. So actually here I can just run it from here. So the URL checker is the next class. All of these are subclasses, as you can see over here, and you can see URL checker and URL checker activity. URL checker activity is the main class that's going to run threads of URL checker. So we're going to run threads for each one of the URLs we're going to check. So if I click on the thing here, there's a 1, 2, 3, 4 URLs. So when we run the method to check them, it's going to create 4 threads. They're going to be running as a callable thread. They're going to have a return value. So once they've all run, it doesn't really matter what order they run in. Each one of them is going to check one of these things. It's going to come back with the status. So if I click on the check, I've got this one here, Android tutorials good, which was the first one, and then we have the second one here, which is going to be it's the forward. Got forwarded somewhere. This one here was bad. This one here was illegal. It was an illegal thread. I mean, so each one of the, because it's misspelled here. This one here wasn't the correct. This one here is the same one, but it's got a Q on the end of it, so it's a incorrect spelling. So it ran a 1, 2, 3, 4 of them that came back, and then each one of them that came back kind of, this order could actually differ depending upon. Actually, the order did differ here, actually, because they're not running one after the other. They're running simultaneously, and they're synchronized. And so when they come back, they're going to return the values back. But it's basically demonstrating the callable versus the runnable environment. So we can use lower level threading to say that the thread.start, and some runnable thread's going to start. And then we're going to implement thread T is going to be equal to the new thread, some runnable thread, and then t.start. And then we can extend the thread by putting the thread into a thread subclass and instantiating that one, calling it this way. So some thread T equals new thread from some thread. And advanced softwares don't really need to do this. I wanted to show you the threading, but we can do it for new schedule. We can schedule threads, run threads, fix thread pool counts, cache the threads, create new single threads, execute services. We can stop the thread. Why do we want to do that? If something is hung or not doing something. So stopping a thread, private volatile thread running. So compiles on multi-core systems often optimized to prevent changes to variables. Let's see, nasty synchronization bugs, where we can actually introduce a ton of synchronization issues depending upon how we've designed the logic of the program. So don't necessarily need to deal with that either. So the second part of this actually relates to activities in terms of what's going on. So if you want to at a lower, I'm just trying to introduce you to the concept that you can actually run Java threads and synchronize those threads. If you want to look at the code for this, it's all spelled out actually quite simply. This one here is just a class that opens up and reads a URL to see if it's reachable, approachable, and it comes back with the status that's associated with it. And then it's being run by this activity here, and the URL checker that's going to create different threads. And when it creates the different threads, it's going to run each one of the threads is going to work on each one of the URLs that's in the list. And then it's going to come back with the results, and it's demonstrating the callable method from that. So part 2 is really a short one. Looking at in terms of the GUI updates and guidelines for the multiple threads. So updating the UI after threads complete instead of doing it while they do, and downloading images from the internet and using the UI with the view post and synchronous tasks. Which works with the same set of examples actually. This is just a continuation. So non-responsive GUI controls, long-running code in main thread will make GUI non-responsive. If you have a thread that's out there that's associated with an activity that's running the GUI, and the thread's doing something that is time-consuming, it's going to make the GUI run non-responsive. So this is probably the #1 reason why people bother with threads. Why do you need to know about that? You don't need to program with threads at all for any Android application. However, if you want to tweak and make the application run faster and make it run more efficiently, if you have a long process, create a thread, let it run in the background, because you can have background and foreground threads running. Foreground thread's going to run the GUI, the background thread's going to run all the extensive processing that you have to do. So if your thread's going to go out to the internet location and download a picture and do something, and then eventually when the picture's downloaded, you're going to add it to the GUI, then your GUI's not going to be sitting there waiting for the picture to download. So you see this with maps all the time as well. Are you going to wait for the map service to get contacted? Anything that uses the internet, it's going to run slowly until the activity actually occurs and finishes. Why not just create a thread for that, let that happen? It doesn't affect your GUI, so your activity that's controlling your GUI isn't going to be slowed down by any extra activities that are going on that are supporting the GUI. Threads cannot update the user interface. So the background threads are prohibited from updating the UI. So you don't want to use the thread, you want to return the value from the thread, take that value, take that argument, and then update the GUI. So threads are worker bees, background processes and worker bees. So non-responsive GUI control is a problem with that. You have the long running code in the main. So you don't use threads. In fact, you just make one activity and you're going to have it running. And if they have a button and on-click handles takes 5 seconds, then none of the other controls will respond for another 5 seconds. So you're waiting, you clicked on it and you're waiting for something to happen. Nothing else is going to work. So it could, depending upon what the activity is doing, it could cause your user to think that the app is frozen. It's because it's going out to the internet, it's loading up a web page before it actually shows you the page or something, or it's doing something that's going to be time consuming. The solution to that is to move the time consuming operation to a background thread. Have the background thread be doing that so it doesn't affect the user's control over the UI. Which is interesting, you see this in apps when you press a button and then immediately nothing happens but you're able to press other buttons. And then eventually that little screen comes up, like 2 or 3 minutes later or something, or a minute later. All of a sudden the screen comes up and it looks like, oh wait a minute, I don't know why I didn't see that originally, but now it's here. Well, you didn't see it originally because it was loading. What was it doing? It was doing a heavy-duty search or something, some translation of something, and then finally it finished. So it triggered to the active running thread that, hey, I'm done, so let's show the code now. So open up the window now. So move it to the background. This entire point of the previous lecture on the basic thread concept. So this is the reason why you're looking at threads, actually, so you can make background processes. So threads can't update the UI. So the problem is background threads are prohibited from updating the UI. Only the foreground process can do that. Background threads cannot add a new view to the display, nor can they tell a text view on a visible view to do something or call it, change it. So the solution alternative is wait until all the threads are done, then update the UI. So when multi-threading improves performance, but total wait time is smaller, so theoretically. Well, because nothing's happening, the processing you're getting on the foreground on the UI causes the CPU to work. So if you're going to wait and then update that, then you have more processing time for the background threads, then the whole entire application is going to run faster for you. Have the background threads use the view.post to send UI updating operation back to the UI thread, and especially when transitioning standard thread code to Android code. It might come in handy. And also the other alternative to that is to use a async task to divide out the task among the background and the UI threads, especially when developing an Android app from the beginning and you have lots of incremental GUI updates to happen. So updating the UI after the completed threads, that's what we just looked at. This option that goes out and checks all of the URLs, runs all those threads, checks all the status, takes all the status after everything's been finished, and then updates the UI with it. So scenario is using threads to improve performance. And then the wait time is smaller, no need to display individual results. If you displayed it after each one of the threads finished, then the threads would be updating the display appropriately, probably. So add threads to the execute service task list, and then wait for the termination on the threads. So you can tell when the thread is stopped, when all threads have stopped, then continue. And then update the UI. So then the UI updating gets safe and legal. So example would be multiple URL validator. That's the one we just looked at a few minutes ago. So the idea is let the user enter in multiple URLs, click on it. So click on the legal by making the head request and check the server status line. And then the approach is to make the URL a list in the list holder so the list shows up at the end. So use the URL pass results that come back through along with the status and then update it all together. So the code for it looks like this. There's a list. We have a list view adapter that we're using in a linear layout that's going to have a list, an array list of all of the different items from the URL checker. URL checker is going to be the one that we looked at over here. Each one of these guys is running a separate thread, and then this activity is going to be updating it. So. And then the button handler. The button handler is simply going to spark the run the threads. So it's going to check the URLs. So it's going to make the instances of the URL checker. And here our URL checker result. That's going to come back. The checker result actually works with it. It's the one right here. That's going to formulate the string that's going to have all of the results from all of the running threads. So if we have 5 of them, we have 4 of them, it doesn't really matter what we have. This is going to put it all together into our list adapter for us. So using our array list, actually that's going to store it. So the button handler after the thread's complete is going to be my results. I add view. I'm going to add view. We're going to display the results, and the display results are going to come out of the UI URL checker and the results that are going to be returned from it. And then we have the Runnable inner class for the URL tester. That's going to bring implement to Runnable. That's going to create the multiple threads for us. And then the URL checker result is going to be equal to URL checker. We'll take that entire string that we have in the upper box where the user typed in the URLs, pass it over, and then set the result URL back to results. And when we get the results back from that, then we're going to display it to the screen again. So it's fairly straightforward. There's a couple of helper methods for it. Choosing color, drawable icons. And let's take a look here at the example. Coming back again. The last 2 parts of it, this is the URL checker, that's the second part of it. The image downloader is basically going to demonstrate how this thread's going to go out and get it, but we're not going to wait, so we can download the image and then we can download the image. Oh, do we have internet access? This should, oh, there it is. It downloaded the image. So, but the UI wasn't frozen actually. Oops, I just froze it. There we go. Because it tried to update it. So this one you're supposed to be able to, it's waiting until the button is going to call the thread that's going to download the image, and then it's going to release it so that the UI doesn't actually, so when you click the button, then you can click the button again, you can see the button itself be responsive to a certain point. At one point though, it does interrupt when the background thread stops and presents the image. It's going to be updated. The other one, oh, that's the no-threaded example. So the UI should have stopped on that, which actually did. Yeah, see how it well, you can't see it from looking at it. You can't see it, but it does freeze on me. My mouse gets stuck, which I actually did experience. And then we have the one where it should not get stuck. Yeah, see, it doesn't get stuck. I can click the button as many times as I want, and the UI is still responsive. Unfortunately, every time I click that button, it starts the process all over again. So it kills the thread and starts it over again. This is basically downloading 5 images. But I can click it again, and it's responsive. If, for example, I didn't want to, here's actually a good example is a search engine that's going to come back with thousands of results, and you want to stop it. If you don't thread it, you can't stop it. Here we have these images that are downloading, but I could stop it. Whoops. Now it's running fast because it's cached, but I can stop the download on it. And then the other one is going to be a variation on that. I believe one of them separates out the class and synchronizes it, and then the other one, oh, this is going to do them all in one batch. Yeah, this is going to wait until they're all done and present them all instead of doing them separately. Oh, no, it didn't. It should wait, get them all, and yeah, put them all simultaneously instead of doing them all individually. So one of them, each thread, when each thread ends, it updates the UI. The other one waits till all threads ends and then updates the UI, so, which are going to be the different variations. So, which is the tail end of this code here. So here's a little helper thing in URL checker. Let's see. So let me catch up with the PowerPoint in terms of the examples I just gave you. So the checker is going to essentially update the UI at the end. So, downloading the web images. The idea is to create a decode stream method for the bit factory. Downloads the pictures, puts them into a bitmap image. So you can put the bitmap images and put into an image view. We've actually seen this in another example, so don't necessarily need to go through the implementation of it. The approach is to get an HTTP URL connection and take that from the, get the input stream from that connection, create the bitmap image from the bitmap factory, and then update the UI view with it, image view with it. So I'm going to skip through the idea of getting it because we've seen this before actually. But given the address here, we're going to try to load the bitmap image from it. So here's our images that we're going to find given the address that we put in there. So the unthreaded image viewer does it, so it lets the enter in the URL and then click and display it. Either shows the image or shows an error. So, which is what we've done actually before. So we can do a view post, which is after each one of the threads, it's basically coming back when the thread finishes for each one of the images that it's downloading. We'll come back and do a view.post, which updates, so the thread ends and updates the post, updates the view. So the wait time might be longer, so you can show any intermediate results after each one instead of showing all of them together. The second example waits and shows them all together. So it's basically providing you, and I'm not going to bother you with the rest of this code because it's actually kind of dry, basically what you want to do is separate the button handler out so the button handler is only handling the running of the threads, initiating the running of the threads. Let the threads handle themselves so that when the threads finish, either after each one of the threads or after all of the threads, it updates the UI by sending a view post, which will automatically come back and communicate with the UI. And then if you put it off on a separate thread, depending upon how long the task takes, it doesn't freeze the UI. So the reason why you're looking at this is that you want to basically create a smoother interface, smoother running user interface. So the results are going to essentially be showing you all of the things I just showed you a few minutes ago. So. Now I know that was kind of quick, but that was your brief introduction to threads as they apply to Android, which is very similar to Java. So it's not the replacement for a Java programming course in threads, because that's like an entire week normally, or 2 weeks of programming. And you'll get a little bit of the thread stuff in the Java programming class if you're taking that one. But long story short, the same concepts apply to Android. So I guess I could have just said, hey, everything you know about threads in Java? Same thing with the Android. But we use them for different purposes. In Android, you're using it to create more responsiveness. There's absolutely no reason why you need to program in threads outside of being able to control how smooth the interface is running and how things are working in terms of the synchronization of tasks and things that are going on. And to take long processing and break it out into more manageable kind of threads that can either fail and catch them on their own, and then you can do a little bit better troubleshooting. If you have everything running in one thread and something doesn't work, like the URL is missing, you have to wait for the whole thing to time out, which means your app is going to sit there. And there's some apps out there that do that just sit there. And you're like, what's wrong with this? It's frozen. Well, because it's doing something that probably should have been put into a background process so that the front end doesn't look like it's frozen. Essentially, all of it's frozen, but you don't want to give the user that opinion or that impression. So, questions about threads? No? Okay, well, we have more stuff to do, but we'll do it after lunch. How's that? I think it's time for a lunch break. So let me end this video.